All right, there we go. All right, so are we okay to hear, Trev?
Yeah.
Okay, so fire up the calculator and get in. Okay, so let's do that. Again, when I type this into my calculator, I like to use the fraction option here because it's easy to make sure that I'm doing what I'm supposed to be doing because it's going to look exactly like I wrote it on the sheet of paper, which is a pretty good deal. So when I do that, I get 100.95. Now, once I have one answer, I can either use the law of cosines again in the same fashion, or I could do the law of sines to find the next angle. It doesn't really matter which one I do, and doesn't matter which angle I solve for next. So just for the sake of doing something different, let's do the law of sines. So I'll do sine of angle y over y is equal to sine of angle x over x. So when I cross multiply, divide, and then take the sine inverse, I get x is equal to the sine inverse of 5 times sine of 100.95 divided by 12. So sine inverse of fraction 5 times sine of, and I'm just going to use the answer command to use my previous result so I don't have to type that all in again. And there I get 24.15. And then to get z, I can just do 180 minus y minus x. Okay there, Trev? Okay. Yeah, I mean, that happens, man. You know? I get it. You're doing that goose thing again. So 54.90 would be the last one. Does anybody else have questions from this assignment? Okay. Hopefully these went fairly well. Again, I don't think that this is a particularly devastatingly difficult chapter, but it is definitely, there's some little tricks involved, and if you haven't done, you have to be a little bit careful doing the problems, but the steps involved are usually not difficult steps, although there's kind of a lot of things to remember. But it's certainly nowhere near as conceptual as some of the things first semester was, right? This is a little bit more straightforward. So what I'm passing out right now is a little activity that we're going to do together in deriving the law of cosines. Well, that's where the formula comes from. Aren't you curious about why the formula works? Not even a little bit?
Not at the moment. Deriving the program. This is what are you the teacher?
You mean deriving the quadratic formula?
Yeah.
Where you have to do the completing the square?
Forget I said that.
I don't know, man. I think that...
We're not going to have to derive that.
Yeah, right?
No.
Then yes, I'm interested.
But here's the thing, guys. This is the crux of most mathematics. Yeah, the thing that you're most interested in as a mathematician is can I discover something new? And what does that look like? It's a proof. You're doing a derivation. You've discovered something that we didn't previously know. Right, fair, but Just like you might not classify yourself a writer either, but you have to like experience what writing is like and create something new, right? Even if you don't want to be a writer. You know, it's the same kind of thing. You have to see what the discipline is like. You know, whether you're a historian or an economist or a psychologist or whatever, if you take these courses, you kind of get an idea of what, you know, the people that spend their life devoted to this study are interested in doing. Does that make any sense? Okay. So let's take a look at this sheet. We all have one of these. We're going to kind of just do this together. So remember yesterday. Oh, well, let's first look at what we want to try to prove. So we want to prove this equation, right? That's what we're asked to do. Okay. Remember back to yesterday, we observed that this equation looks a little bit like something else. Looks a little bit like the Pythagorean Theorem. Great. In order to use the Pythagorean Theorem, what do we have to have? Right triangle. Okay? Do we have a right triangle in our picture? No. So the first thing that we're going to do is we're going to want to divide this triangle into two right triangles. Now there's three ways to do this, whether you draw your altitude from vertex A, from vertex B, or from vertex C. So let's think about which of these angles we're the most interested in. Look at the equation. Which angle are we the most interested in? A. So where would we not want to draw our altitude from? A, because we don't want to cut that in half. We want all of angle A available to us, right? It doesn't really matter now whether we draw our altitude from angle B or angle C, but there's definitely one that's going to make our life a little bit easier than the other. No. It's going to be B. I'm sorry. That's what I meant. Whatever we said. This is the one you want to use. Did I say the wrong thing? I apologize. Yeah, I don't know. I gotten like less than 4 hours of sleep for like 3 weeks, so it's not functioning at maximum capacity right now. All right. So we have two triangles now, triangle 1 and triangle 2. Everybody good with this? So let's look at triangle 1. In order to use the Pythagorean theorem, we need to know the length of the legs, right? What is going to be the length of the leg, or of the base, I should say, for triangle 1? Hi, Ben. Thanks, bro. So you should be able to express it with just one letter. So we're talking about that length right there. Yeah, of course, dude. What do you guys think? X. Yes. Why X? Well, that's you have the right answer for a pretty lousy reason. So let's really worry, Raul. Yeah, so the thing that we weren't looking at were these coordinates. Right? So if C is the point XY, that side is definitely X, right? What's going to be the height of triangle 1 then? Y. Okay. Now, what's the base for triangle 2? C minus X. Does everybody agree there? What's up? It's recording right now. So yeah, we will. All right. Now, write the Pythagorean theorem for triangle 1 and write the Pythagorean theorem from triangle 2. Do this now. So what did you guys write for triangle 1? Good. What did you write for triangle 2 then? Okay. Everybody's good with those. Look at these two equations. Do you see something in common?
There's 2y squared.
We see y squareds. So what we're going to do is we're going to think about this as a system of two equations. And we're going to make a substitution. I'm going to substitute one of these equations into the other using that y squared. So if I call this equation A and this equation B, which one am I plugging into the other? Does it matter? No. Is there a choice that's better than the other? Yes. So look at again what we're trying to prove. Do you see any part of that in either of these two equations? I see the a squared by itself already in that equation B. Did you guys notice that? So my goal is going to be to substitute equation A into equation B, so I keep that a squared by itself. Is that cool? So I would just rewrite this as y squared equals b squared minus x. And then when I plug equation A into equation B, I'd have a squared equals b squared minus x squared plus c minus x squared. Is everybody okay with the substitution that we made there? Now I moved, like I flipped some of those equations, right, them forwards and backwards there a little bit just to make it a little bit nicer, but don't get thrown off by that. I just moved where the equal sign was, right? Everybody sees that? Okay. Now again, let's compare to what we had before. So we have the a squared by itself. We have a b squared. So I'm not going to change either of those two things because they're what are supposed to appear in the final answer that we're looking for, right? But somehow we have to manipulate the rest of the stuff. So what do you think we should do next? What do we want to do next? What was that? Great. So let's expand c minus x squared. To do that, you have to FOIL, right? So we'll get c squared minus 2cx plus x squared. if we combine like terms, what do you notice happens? Yeah, the x squareds cancel out. And now we have almost exactly our law of cosines, right? The only difference is here we have an x, and here we have b cosine A. Everybody see the difference there? So somehow I should be able to show that x is equal to b cosine A. Everybody's okay with that? Look at the picture here. Do you see a triangle that contains both x and angle, contains b, x, and angle A? Triangle 1 contains side B, side X, and angle A. Is there a relationship between side X, side B, and angle A? In particular, the fact that we have a right triangle. Yeah, that is cosine, right? Inside of a right triangle, cosine is equal to adjacent over hypotenuse. Everybody good with that? Okay. So if I multiply both sides by b, I get that x is equal to b times cosine A. Everybody good with that? So if we go back down here and we substitute that in, we have exactly what we need. What do you guys think? Not as bad as maybe you thought, right? I think this proof is actually a little easier than the law of sines proof. Or at least